Okay. Yeah. Yeah, that was a break for you guys. I'm sure it's been a long day. But one more to go, and then you're off for the poster session and I guess the dinner. So thanks for sticking around and being so many. I didn't know that there's going to be so many of you. This is very, very good, exciting. My name is Teemu Roos. I'm from the neighboring university, University of Helsinki, and we work with the physics folks that I'm sure many of you know there, namely Kai Nordlund's and Fjula Durabekovac's group at the Department of Physics. I'm a computer scientist myself, as you will be able to tell when I speak about physics. What we've been doing is combining machine learning with certain simulation techniques for the design of materials. So I guess that's why I was invited to speak here. So very briefly, I'll skim through the physics bit in order to not embarrass myself too much. The problems that we're looking at are simulation of material properties in extreme heat and radiation circumstances, like potentially even fusion reactors and particle accelerators. And what we'd like to do is large-scale simulation of, hopefully thousands of atoms for extended periods of time, like not only a couple microseconds maybe, to see that they actually endure in the circumstances where we're anticipating their use. And the problem there is that even though the kind of quantum mechanical basis for the behavior of the materials and the interaction of the atoms in the materials is apparently well known, that's what I've been told, they are quite heavy computationally to simulate. And that's the kind of, that's our idea here, is to not really do, let's say, experimentation and learning of physical constants or any parameters of the models or the materials from experiments, which would be maybe the first kind of idea of an application of machine learning in physics. We are actually using machine learning to simulate things faster. So we're kind of trying to bypass the slow computations by plugging in a machine learning component that is much faster to use and to obtain the physical quantities that we want. And in particular, we'd like to do something called kinetic Monte Carlo, which probably you guys are familiar with. So let me use an example and a figure to illustrate what I'd like to be able to do here. So we are studying materials that have a crystal structure that can be characterized by a symmetric and regular lattice. Depending on the material, the lattice could have different shapes, but that's not important for the problem, as long as it's a regular lattice, and we can basically enumerate where the atoms are sitting in the bulk of the material. And we will look at one atom and consider a situation where the next position, the next position in the lattice to that particular atom is vacant. So there's an empty gap, empty slot there, and the atom has sort of the chance, so to speak, to jump into that, to occupy that vacancy, right? So you can think of it either way. You can think of it like the atoms jumping to fill the vacancies, or you can even think of the vacancies sort of moving about. Maybe that's a simpler way to think about it. And it's called kinetic Monte Carlo vacancy migration. And in the illustration on the left, there's the blue ball is an atom of a particular element. And it's got about a bunch of neighbors in the lattice, and then next to it, this is the case where the red circle signifies a vacancy, an empty slot in the structure. And And in order for the atom to move to occupy that vacancy, it will usually have to overcome a potential energy barrier, because any position where it is not sitting nicely in its position in the lattice, it is higher potential energy. So there's a resistance, so to speak, that's trying to keep the atom in its current position. And that's what we're talking about, this potential energy, it should be potential, right? Potential energy barrier that is between the two atoms, so to speak. And the higher that is, the less likely it is that that atom should jump in that position. And different configurations of atoms imply different barriers. And these kind of drive the dynamics of the simulation. Okay. And these potential energy barriers are some things that we can at least approximate extremely well with known physical models based on quantum mechanics. I won't be able to list what those are. List what those are. I can look them up if you're interested, or you can probably figure them out from the rest. But nonetheless, there are these three-letter acronyms usually that you use. TLAs. Well, that's the method. Okay, but they are slow, as I said, and we'd like to bypass that part with a method that's much faster. And here's the kind of the architecture. Let's sort of we'll sort of look at one part of that at a time. Let me see if I have a pointer here. Yes, I'm not sure if anybody can see that, but nonetheless, I will wave it around. We've got this. We've got basically the simulation architecture, this whole thing. So we'd like to simulate the molecular dynamics here by being able to calculate those barriers. But that process is an extremely slow one, because if you want to calculate those barrier values, and a hell of a lot of them, to simulate all the possible jumps that the atoms could take at any given time, it's going to take hours and hours to simulate even one single event of an atom changing place. So we'll put in the middle a part, a machine learning component that can, if you're looking at the rider part of this diagram now, it can do the same thing. It can simulate these quantum mechanical calculations that are extremely slow. It can simulate them extremely rapidly. It is kind of a replacement or a substitute or a proxy to this very slow computation. And of course, sometimes the machine learning algorithm just doesn't pop into existence by a snap of the fingers. We'll have to train that somehow, and for that we need to use the actual sort of the slower procedure for calculating those values. And that would be the slow process of sending requests to this calculation module that were given, and then calculating those barrier values and updating your machine learning component. And now our idea here, this is the kind of otherwise this would be kind of pretty standard approach. Our approach here is that we'll combine these things. We'll put them together, and we'll basically put inside this big simulation here, we'll put the machine learning algorithm that has access to this slow computational procedure. And it will only obtain more data if it is not able to produce good approximations of those barriers, right? So it will train itself, or it will request more data that it can be trained on only when it needs that. And therefore, we don't have to worry about calculating a huge amount of training data for that machine learning algorithm if we don't need that. And that's kind of our new idea here. Right. So that's summarizing in words, I guess. It would be quite slow, of course, to train the model with a big amount of training data, which we'd like to do. And it's sort of choosing random configurations of the atoms in the lattice is quite wasteful. It's not going to be the most useful, most informative training set that you could imagine. And therefore, we'd like to choose smartly. Okay, so we'd like to choose the right training data that is going to be useful for our simulation. Okay, so some of the configurations are really weird, unlikely to occur in the simulation. So we don't need to train on them. We don't need to know what is the jump probability if in a very exotic, strange, or anomalous configuration. We need to be able to produce those barrier values for the configurations that are likely to occur multiple times in the simulation. And that's what I mean by choose smartly. And in machine learning lingo, this would be called active learning. So you train only when you need to, and you train on the data that you find the most useful. And in order to do that, as a sort of, for me, like a machine learning guy, it's interesting that this works. This can be done only if the model can kind of self-diagnose. If the model can tell, oh, okay, I can actually predict that barrier value pretty well, but that one not so well. So it needs to be able to assign uncertainty to the particular configuration that we're asking it to predict, or the uncertainty related to that barrier, related to the barrier for the configurations. So it's not enough that the system can tell, I can predict with, this and that variance. So the overall variance of the predictions, or the standard error of the predictions is such and such. It should be able to tell that for this one, I'm good, for that one, I'm not. And therefore, it can choose more data to then get better at the other thing. And most existing neural network-based methods that have been used in this problem, there's already some published literature on this problem that people have used, had the kind of problem that they couldn't do that. So we wouldn't be able to, we wouldn't be able to plug them in here, because here it is key that the algorithm decides for some configurations that it'll get more data, and for some configurations it can just spit out the prediction without accessing more data. And if it always says that the error is going to be a fixed amount, if it gets this overall error that you can easily get by just running it on a set of test data, if it always says the same error bound, then you can't do that decision based on the configuration that is in the simulation. Okay. Okay, and then in case you're interested about which methods we'd be using, we were using, or we're using and studying, we've tried quite a few of them, but we found that sparse Gaussian processes are a very good technique for this, because they inherently, their kind of built-in functionality is that they can spit out the uncertainty estimate. So here's an example of a sparse Gaussian process where you train with just a few points here. It's hard to see there's a couple points here, 5 points here, and around those points, the model predicts very narrow, sort of high probability intervals. So that's a Bayesian method. So it can kind of quantify uncertainty very naturally. Whereas far from those training data points, it is reasonable that it is very uncertain about what is the actual outcome. So it will say that here it could be basically anything. And when you get more data, it will still have some uncertainty, and that uncertainty depends on the kind of the variance, local variance within that region of data. And this is just simple one-dimensional case, but you can imagine in high dimensions it'd be quite interesting. And here's just a couple examples of the actual, so the previous one was just example one-dimensional data. Here we have the actual barrier values that we're predicting that have been calculated. The horizontal value on the horizontal axis, you have the actual calculated value from that very slow quantum mechanical computation, and the predicted one is on the vertical axis. So you can say that it's not if in the ideal perfect case it would be all on the diagonal, but now we have some error either up or down in the predicted barrier values. And you can also see some things about the distribution. There's quite a bit of stuff at zero, so there's very low barrier values. Could be even that there's no barrier, in which case you can imagine that the atom will just sort of automatically roll to the next position because there's no barrier between them. And these are two methods. They're extremely similar in accuracy. On the left, we've got the neural network. On the right, we've got the Gaussian process. But from the Gaussian process, we have the uncertainty estimates, and that's the good thing. And that's why we're quite keen on using that. There's another approach based on neural networks that can produce those uncertainty intervals, and I'll talk about that now. So the best method that we found so far is actually not the Gaussian process, even though that's kind of theoretically very appealing and a nice Bayesian method. I noticed there's a lot of Bayesian here, so that's great. But nonetheless, we found that currently the best performing method we have is based on two neural networks, and that's an interesting construction. It's not it's not our idea. I think we got the idea independently, but we noticed that other people have had the same idea as well. And the idea is that you have one neural network that predicts the value. So one neural network is going to spit out that value here, and that's going to say that, let's say that the barrier is going to be, 0.9 or something. And then you have another neural network which is going to spit an uncertainty estimate, or a sort of expected error for that particular prediction. And you can sort of bundle them together and train them using a nice construction with cross entropy and stuff, and that seems to work pretty nicely. And it's all implemented in PyTorch, so we don't really have to work with the calculating any gradients. The machines, they will do that for us. These are very nice tools nowadays, similar to TensorFlow and stuff. I'm sure many of you know them. And we just bundle that together with the KMC simulator, which is another sort of hassle, of course, to combine two different software systems. But that's what we did, and behold, it actually works. That's the good news. Actually, there is a question: does it really work? But it seems to work. Let's say I'll be a little more modest on my statement. It seems to work because when we started with this configuration, we have a surface, and there's this weird cube of molecules or of atoms standing on top of that flat surface. And then when we start the simulation, we will see that it flattens out nicely and it depends. This is the surface. On different surfaces, apparently, it is natural to expect that there's different behaviors in the simulation. And so this can be sort of, I believe, or I've been told, that this can be to some extent experimentally verified, that this is what actually happens. And when we see that it also happens in simulation, then we can claim that in this scenario at least it seems to work. Okay. So that's our only way of testing whether these systems actually work, whether the fact that we're not doing the quantum mechanical exact calculation, which is slow, but we're kind of replacing that by the machine learning proxy, that doesn't distort the results too much. We can't really run the simulation with this slow exact process because it really is too slow. Otherwise, of course, we wouldn't do the whole thing. So we can't really compare to this exact method. We can compare somehow experimentally to actual physics, what actually happens, but not on this sort of. We can't, of course, construct exactly these structures because you can't just manipulate atoms with that precision. Or I guess it might be possible, but it actually be very, very slow and tedious. So the only thing we have is a kind of a general understanding that this is the physics and that looks natural. If now this is my call for action for you guys. If you have any good ideas of which kind of configurations we should experiment with, and we should simulate, so that we would see that it actually produces some natural and realistic simulation behaviors, I'm all ears, because that's the kind of missing thing for me to really say that it works, that we'd be able to prove that it produces physically realistic simulations. We're kind of it's sort of bothering me how, let's say, qualitative physics we're doing here. If you, it's like you'd think that physics is a quantitative science, but we're kind of doing qualitative research here. A couple examples, and we're looking at it and saying, well, it looks kind of reasonable. Right? And I'd like to be more precise. I'd like to be more quantitative about this. I'd like to be able to say, give out a number how good it was. And if you have any ideas how to do that, I'm all ears. And I think I might have a fun simulation here. Let's see if it works. Yeah. So, yeah, that's how it looks basically. There's an interesting thing. I don't know if you see that, but somewhere it starts jumping a bit. Not yet, not yet, not yet, but just about here. Yeah, and another one, boom. And this is something we're trying to understand why that happens, and that's apparently an artifact of the simulation and the active learning system. Apparently, it gets a little bit too confident about its predictions at some point, and it starts to generate strange configurations. So the atoms start behaving a little bit unusually, and then it runs into a space where it doesn't know what's going to happen. Right? It encounters those areas where the model self-diagnoses itself as being a poor predictor of what's going to happen next. And then it starts to loop back to this slow process. And it gets very good predictions. And then it settles down. And then it does that for a while, and then again, at some point it starts to get too confident and makes errors, and then those errors bring it again to those sort of unusual configurations. And then it notices that, oh, I don't know what's going to happen again, and then again it falls back to that exact calculation. So that's our theory of what happens here, but maybe that's a kind of a little bit of a sidetrack. Just does that jumping. So that's actually where we are. That's all I have to give you. I don't have like a new material, or you don't have the fusion reactor wall design yet. We're working on that. I can only offer you answers to your questions if you have any.
One there. Oops.
Thanks. So before you can evaluate the barriers, you need to have a suggestion for the process at all. So how do you get the suggestions for your processes? I suppose the whole thing is on a lattice. But
yes,
also,
so
I mean, you could have fairly complicated processes involving 10 atoms moving at the same time and so on.
All right. So what
we need suggestions.
That's right. So we live in a very sort of constrained. In a way it's discrete setup. We don't allow the atoms to float around. So we're not representing the material using coordinates of the atoms. We're kind of enumerating: is there somebody here? Which element is it? And if there's not, then what is the next position? So it's kind of our whole thing here is a discrete representation of the material. And then we allow only one jump to take place at a time. Of course, the time interval at which it takes can vary. So that's the KMC framework that we're employing. So we have this discrete representation. There's some vacancies. There's multiple different elements. And we ask, which is the next transition going to happen? From which point in the lattice it moves to the next? Did that answer the question?
Yes.
So we're kind of constraining really heavily the composition of the material. It's not like the molecular structures that I think the previous talk was talking about with coordinates and continuous valued representations.
But you could have many exchange processes and so on in reality, of course.
Of course, yes,
yeah.
yes. We just simplify and say that only one atom gets to move at a time. But of course, the next atom can move very rapidly after that. It depends on the simulation. It's kind of stochastic, so can happen.
Another question.
There was a question, I think, right here.
Yes.
The-
Okay, let's go on.
I have a fast question. So you say you use a neural network to predict the error on the energy.
Yeah.
But if you use a neural network to predict the error, but you train on it, how can you be certain of its prediction in areas where you actually need the error, so the areas you didn't visit? Because you train it using training points, and so a neural network is as good as
That's a good question. So I'm not sure. Like, probably there is no guarantee that the system is going to be able to say that in an area where it has no training data, it should produce a high error estimate, because there's no guarantees of prediction there. But how, the question is, I guess, how does the other neural network then know that it should say, I don't know?
Yeah. Gaussian processes do automatically that.
Gaussian process has that inherent ability to do that, and the neural network, it has to be kind of built into that. I don't have an answer to that question. I just know that it seems to produce a slightly better calibrated, that's the technical term, better calibrated error estimates than the Gaussian process. But I'm not sure like how it actually manages to do that.
Okay, interesting. Thanks.
And this will relate to the fact that the action process gives actually some uncertainty rather than an error estimate. So they are slightly different, right? So one is actually tuned on the error you make. The other is more, you can have someone said that even before, and in this session, you can have a very low error and a high uncertainty. That's totally fine. While if you fit on the error, and then you don't have this problem. That could be another issue.
Yeah, I think but in the end, I think they both produce a normal distribution with a certain variance. And sort of having thought 5 seconds more about the previous question, I think I think the key is that you don't train them separately. You train them together with an entropy loss, so that the cost function that we're optimizing actually would penalize if the system starts predicting accurately in areas where you have no training data. So it will actually have this kind of default prediction, which is a very high variance prediction in areas where it hasn't seen anything. And only if it has seen some data there, it will shrink that. So I think that's the explanation of how that can actually work. So you don't train them separately, you train them, you just sort of put them together and optimize them both. But the good thing is that these tools allowed you to do that pretty conveniently. Yeah, there was this one.
So thank you for your presentation. And could you go back to this slide about the proposed approach when you showed it? Yes.
Yeah.
So about this data request,
yes.
How, it's kind of two questions, but how your code knows exactly when request more data?
Yeah.
And
yeah,
what's
that's
the amount of this new data you should have? Because, I mean, one configuration probably is not enough from the statistical point of view.
Yeah.
So how many new data you should add to your code?
Actually, one is usually... One might well be enough, because if we are uncertain about the particular jump probability, we want to know what is the probability, or what is the kind of actually what we calculate is the expected time it takes before a jump takes place. So what is the rate or that expected time in a particular configuration, and then the system self-diagnoses and says, I don't know, it can actually go and calculate that very configuration and that very jump probability. And then of course we can pretend that we know exactly what it is, and we can proceed with the simulation. The other question is, when do we, or the first question I guess, was that when do we then decide that is not good enough? And that's actually a very hard question. We don't really have a theoretically sound answer to that. We're just using a heuristic that if the barrier is within that margin, then we just pretend that it's good enough. And if the error is above a certain margin, then we go and sort of actually calculate that with the slow procedure. And that's a kind of a hyperparameter, a tuning parameter to the whole framework. We're trying to come up with certain sort of more rigorous methods to decide that, and we can have some ideas for doing that in terms of mutual information of the jump and the barrier and so on. But we're still in the process of doing that. So, very good question.
I actually also have a question. When you show this dynamics in which you do active learning, and then there is something that maybe gets a bit unphysical because the algorithm is still learning, did you try to run the dynamics again at the end of the cycle to see?
Yes, and it works better.
And
it irons out that jumping around effect. Yes, precisely.
Okay, so if there is no other question, let's thank again Teemu.
Thanks.
And,